Hello everyone. So in this presentation, we will see what is the impact of actually why do we need a layer normalization in transformers or large language models or you can do it in the feed-forward neural networks as well. So we will try to see exactly what kind of implications or what kind of benefits it brings in. So here the goal of layer normalization, right? So layer normalization is crucial in ensuring the variance of activations remains controlled across different layers of a neural network. Okay, this is when I say different layers means it could be a different transformer blocks as well. Okay, so particularly the deep models like transformers. Okay, so this helps in stabilizing the training process by maintaining a consistent scale for activations. So, so basically, the condition number of weight matrices that exist in that layers, right? So, how sensitive those matrices is to changes in the input, especially in terms of a gradient scaling. So, a high condition number means that the gradients can disproportionately amplified or reduced, causing instability in training. Okay, so we will see exactly what is the role of the condition number of any weight matrix. Okay, so it could be key value, any weight matrix that are present in the transformer block or in a feed-forward neural network. Okay, we'll try to understand exactly how they are going to affect the gradients during the backpropagation. So the condition number is nothing but actually the maximum value to the minimum value, maximum eigenvalue to the ratio of maximum eigenvalue to the minimum eigenvalue, or if it is not square, then in that case, it is a maximum singular value to the minimum singular value. Okay. So suppose in order to see the impact of a condition number, right? If we don't use a layer normalization, suppose for example, as we know, if you take a simple layer, a simple affine transformation. So that is Wx plus B kind of layer, simple affine layer. So in that case, so the back propagation, right? The gradient propagation during the back propagation, if you see at layer L, so delta L equals to W transpose delta L plus 1. Okay, that we know, right? Suppose like YL is equals to WXL plus B. It's like a forward transformation is affine transformation at layer L kind of thing. But during the back propagation, the gradient is computed. So delta L is equals to W transpose delta L plus 1, right? So without layer normalization, if the weight matrix has a high condition number, for example, in this case, 10 you can consider. So with this high condition number, the variance of gradients grow as they propagate through layers. So in this example, for example, if we consider condition number 10, the variance of gradients can increase by a factor of 10 across layers, causing gradients to either vanish or explode. Okay, because in this case, the condition number is more than one, so the gradients will explode. But if the condition number is lower than one, the variance might vanish. So, what is the layer normalization's role in stabilizing activation variance? So, as we know, layer normalization basically normalizes the activations. So, by subtracting mean and dividing by the standard deviation, as I shown in the slide. So, which results in activations with a zero mean and unit variance. So, this normalization ensures the gradient magnitude remains consistent, preventing them from becoming too large or too small. So how, suppose, okay. Now how layer normalization controls gradient magnitude, right? So with layer normalization, the gradient magnitudes are bounded because layer normalization stabilizes variance of activations. Okay, without layer normalization, the gradient variance can grow uncontrollably, especially if the weight matrices have high condition numbers, leading to exploding gradients. Okay. So mathematically, the layer normalizations keeps the gradients stable by ensuring that activations are normalized before being passed to the next layer. So without layer normalization, the gradient magnitudes depend directly on the condition number, which leads to instability, right? So that's what is because every before kind of passing to the next layer, right? Always these activations are normalized. So because of that one, the condition number so doesn't impact subsequent layers as we go deeper into the neural network. Because every layer between every two between subsequent layers, there is a normalization layer sits in, which makes it those activations unit variant and zero mean kind of thing. So what is the summary of layer normalization's impact on gradient stability? So layer normalization is essentially in reducing the impact of high condition numbers, ensuring that gradient magnitudes remains bounded and stable throughout the training process, especially in deep neural networks such as transformers. This results in more stable and effective training. Okay, so if we want to summarize it, basically because of this layer normalization, these kind of activation normalization, right? The condition number doesn't influence them much because between every two layers there is a layer normalization six, which maintains unit variance and zero mean kind of thing when it comes to activations. So this is what it does. Hope you got it.